Okay, so we're live on YouTube. I'll just set the permissions.
I should go connect my tea.
Sure. Okay, hi everyone. I think I'll get started. So I'll just remind you that we're in the process of proving a theorem, so a weak law of large numbers for the largest component size in Erdős-Fenyi random graph. So we had so our graph is G and P takes this range. So it's constant over n, and we have some upper bound, which I'll call a on that constant, and the lower bound is a little bit bigger than 1. So we allow some vanishing correction to 1 if we like, but we require that that correction epsilon grows faster than n to the minus a third. So that's necessary for the theorem to hold, as we'll see. So through an analysis of this depth first Q process, we're going to prove this law of large numbers. If you're taking notes, I mean, all of this is written up in the notes, but if you're taking your own notes, you might want to change this. So this upper bound here was called M in the last lecture, but they're going to be Martingales, so I switched it to A. Right. So this is where we're heading, and so we're going to prove that by showing that this process of active vertices closely tracks this curve, which I heuristically explained at the end of last lecture. So the curve n minus t minus ne to the minus pt. So where these terms came from were we were starting with n vertices. At each step we explore exactly one vertex, which gave us this linear correction, and then we discover some random number of new vertices from the collection of previously unexplored vertices ut, and because that exploration was binomially distributed with success probability p, that caused this 1 minus p to the t type decay. Okay, so this was what our heuristic gave us, and so this function xt will come in, but then because it's a little bit nicer to analyze, we also defined ft, where we approximate 1 minus p to the t by e to the minus pt. Okay, and I left as an exercise to show that the difference between these two is uniformly big O1 over the range of parameters that we're interested in. Okay, so that was the setting. We want to show that So what's plotted here is the difference between n minus t and this n e to the minus pt. Okay, so if we can show that the number of active vertices closely tracks that curve until this time n theta of lambda, okay, well then that would suggest that basically between time 0 and time n theta of lambda, we're just exploring one large component, well, one component of the Erdős-Rényi random graph, so that component would then have size about n theta lambda. Okay, so if that were the case, that would sort of prove a lower bound on the largest component size, because we would have found one component of roughly the size. And then we'd like to argue from there that after this time, we don't find any other components that are even larger in the exploration process. Okay, so that's the structure of the proof. So there's a bit of work to make all of that hold together. One first thing we need to address, which I also alluded to last time, is that there is some randomness at the start of the process, which means we're not literally necessarily going to start exploring a large component instantaneously at step 1, right? So that we might have a few false starts at the beginning. And so I'd like to start this lecture by heuristically discussing how the process gets started, so the early stages a little bit more. Okay, so that's how we'll start the lecture, is with the early stage of the process. And so this will be somewhat heuristic, but we'll lean on sort of rigorous bounds that we've previously proved, so I hope it'll feel fairly plausible. Okay, so the key sort of input to the heuristic is the idea that the components, so typical components, we can approximate a typical component by a Poisson biennaimétrie. Okay, with parameter NP, right? And this, this is, well, I'm being vague here, and I need to be vague because it's there are senses in which it's true and senses in which it isn't true. But at least we know that at the start of the process, the number of offspring, the number of neighbors we discover does have the binomial roughly NP distribution, which is roughly Poisson NP, which is roughly Poisson 1 minus epsilon, 1 plus epsilon. So at least at the start of the process, something like this is plausible. And so then you might sort of be willing to accept that the probability that we stumble upon a large component at the start is something like the probability that such a Poisson biennaimétrie is large, and let's use infinite as a proxy for large. Okay, and we saw that was of order epsilon, so up to constant factors here. Okay, so that's all I mean to say by that is that you can imagine that for the first process, that the probability that we get lucky at the very start and the very first component we explore is the large component we're looking for will be of order epsilon. Okay, and so if you sort of will play along with that heuristic for a moment, then that suggests that you expect to explore on the order of 1 on epsilon components before finding the large component, or a large component. Okay, so how many vertices does that mean we're going to explore before we explore a large component? That's, in terms of the time parameter of this process, it's not number of components, it's number of vertices. So how many, if we're going to explore about 1 over epsilon components, how many vertices are we going to uncover before we come across a large component? Well, we have estimates for the sizes of Poisson bien-aimé matrices. So we know that the probability that a tree like this has size S is on the order of 1 on S to the 3/2, when S is at most 1 on epsilon squared. Right? So if epsilon was 0, then this 1 on S to the 3/2 behavior held for all epsilon, and when epsilon was non-zero, then there's some correction that kicks in when S is around 1 on epsilon squared. Okay, and so that suggests that in the first 1 on epsilon components, the number that we expect to explore before finding a large one, then the total number of vertices we find should be roughly, well, let's just use linearity of expectation. So we have 1 on epsilon components, and then if we sum S at most 1 on epsilon squared, S times the probability that a Poisson 1 plus epsilon bien-aimé tree has size S. Okay, then this is, so 1 on epsilon, and then something like S at most 1 on epsilon squared, 1 on S to the half, right? So because we have S and then something of order 1 on S to the 3/2. Okay, and this sum will give us another 1 over epsilon, right? It's integrating S to minus a half up to 1 on epsilon squared. So this whole thing is about 1 on epsilon squared. Okay, so that suggests that if you at least if you're willing to hold your nose and do these quite brutal approximations, then this suggests that we find the large component after about 1 on epsilon squared steps. So there's a question in the chat: does this probability decay rapidly for larger values of S? It does. So we saw that in order to have a fixed finite size S, this in particular has to be a finite tree, and that makes it look like a subcritical bien-aimé tree, and at that point the sort of this you start to get an exponential term that makes these probabilities decay rapidly right after the value 1 on epsilon squared. So that was developed in the exercises as well, but yes, so we really only need to look up to order 1 on epsilon squared. Okay, so that's so we expect on this picture to find large component after around epsilon to the minus 2 steps. Okay, so now I'm going to try to make that a little bit more quantitative and precise. So we'll fix a function omega n tending to infinity, and I'll want it to tend to infinity slowly. So in particular, so much more slowly than omega cubed n. So we know that so the range of epsilon that we're looking at here means that epsilon n to the third tends to infinity. So we're going to want omega to tend to infinity more slowly than that. And then hope our process gets started that it's found a large component will be omega n root n over epsilon. Okay, and this is indeed with this definition then epsilon squared g is, so omega n root n epsilon cubed, which does tend to infinity. And so this time we're looking at is much bigger than 1 on epsilon squared. Okay, so we can hope that at this time g, we should have found a large component. Okay, so that's where we'll hope our process gets started by. And now, here's the theorem that's going to yield our main result. So I'll write z for the number of components that are discovered by time g. Okay, so if you didn't, I should say, if you didn't buy this heuristic, or if you were skeptical about the heuristic, I mean, we're now going to just be doing sort of rigorous math for the rest of the proof. So, if that wasn't helpful to you, you can just forget it and focus on what's coming. So we'll write z for the number of components of GNP explored before time g. Okay, and then so L will be kappa, will be the time at which we finish exploring that last component before time g, and R will be the time when we finish exploring that component. Okay, so then we'll prove that so the component explored between these two times has size n theta of lambda. Okay, so that difference converges in probability to 1 after rescaling by n theta lambda. Okay, so let me give you a picture of that as well. So here's the picture we already had, right? And now here's what the process down below is what the process S looks like. So here's the 0 line, okay? So remember, S is effectively tracking the number of active vertices, but each time S hits a new minimum, that means we've just finished exploring a component. So the times when S hits a new minimum are the times when AT is equal to 0. Okay, so the process goes along, discovering components. At some point, it hits its smallest ever value before this time G, when we hope everything has gotten started, and that's the time L. Okay, and Z. So Z is going to be the depth that we've achieved. So the minimum value that the process has achieved before this time G, because that's the number of components that we've explored. Okay, and then the process will get going, and it'll follow some trajectory, and then our hope is that after sometime around this time D, this component exploration will finish. Okay, and so that so the idea is that this difference here is effectively going to be n theta lambda. Okay, so there's some error that comes from getting going at the start, and there's also going to be some error we'll need to control about where precisely this component exploration ends. But sort of once we know that, but yeah, so that's the route to showing. So this theorem is going to be our route to proving that the largest component indeed has size n theta lambda. Okay, it just says basically whatever component exploration we were in the course of it at this time G, that's what we look at here. We're going to show that one has the target size. Okay, does that goal make sense? Any questions about it? So what I'd like to do is prove the theorem, assuming prove the law of large numbers for the largest component, assuming this fact that we can find one component of the target size just by looking at the component alive at this time G. And then we'll turn to actually proving that this particular component has that size. Okay. So let's prove that let's prove that the size of C max divided by n theta lambda converges to 1, assuming that R minus L on n theta lambda converges to 1. Okay, well, so the lower bound is easy, right? The size of the largest component is at least R minus L, because that was that was precisely the time window on which we explored a component. Okay, and so so this fact gives us the lower bound. Okay, and now so the upper bound isn't very hard. We sort of need to think about two things. We need to think about how big the components were that we explored before this time, and then we need to think about how big the components are that we explore after step R. Okay, so so we'll take those in turn. So we know that so before time g, so how big could a component be? Well, g was omega root n over epsilon. Okay, and we so this is so we choose omega small enough that this is little o of epsilon n, right? Because I said that I wanted omega to be little o of, well, much smaller than epsilon cubed n. So in particular, let's say that it's less than square root of epsilon cubed n. Okay, so with omega this small, then we precisely get a little o epsilon n bound here. Okay, so we can take omega that small. All we needed is that it goes to infinity slowly, or all that we're requiring. Okay, so that implies that components explored before time L. Well, L was the last. So L was the sort of time, the last time before G that we started exploring a new component. So any components that are explored before that time have size at most G, which is little o of epsilon n, okay, which is little o of n theta lambda. Okay, remember theta lambda was is always this is always of order epsilon for the range that we're considering, right? It's about 1 plus 2 epsilon if epsilon is small, and then if epsilon isn't small, then it's bounded away from 0, and so is lambda. So they're both sort of roughly of the same order. Okay, so that says that basically says that this early time here is a smaller order correction to the size n theta lambda. Okay, and now we want to understand what happens after time R. Okay, so let's let so I'm going to give myself a little bit of wiggle room. So let's fix some small delta, okay, and back up here to 1 minus delta n theta lambda. Okay, and I'll call that value. No, I won't give that value a name. So let's say that let's look at so with probability tending to 1, so R is bigger than 1 minus delta n theta lambda, because, you know, with high probability, the difference r minus L we know is bigger than like 1 minus, say, delta over 2 n theta lambda, right? Because we're assuming at the moment that that this ratio converges to 1. Okay, so it'll be bigger than, you know, 1 minus some small constant times times n theta lambda. But we also know that L is little o n theta lambda. Okay, and so r minus L is bigger than this plus a vanishing correction. Okay, and so so that means that R is large. With R is at least this large with high probability. Okay, so this is I should say, so here you know, delta is fixed but arbitrarily small. Okay, so that says that you know, what we have to understand to prove to finish proving an upper bound is the largest component size after this time r. And since we only want the bound to hold with high probability, we can instead study like the largest component size after you know, in a graph that has size whatever is left after this time, 1 minus delta n theta lambda. Because over here we have a random graph which with high probability is smaller than this random graph. And so the largest component in a random graph of sort of this size, whatever's to the right of here, will be smaller than the largest component in a random graph of this size. Okay. Right. And now, so now I'll give myself a name. So let's write n prime for n minus this correction, 1 minus delta n theta of lambda. Okay. So then I'll let well, let me call that n hat, sort of because it sort of has a flavor. It's going to have the flavor of a dual parameter. So we'll let c hat max be the largest component of GNP explored after step R. Okay, so so if you know, we already said that, so we already proved a lower bound, and we said that components before time g didn't push us, you know, didn't give us any components larger than this. So if we can show that there's no components, that all the components explored after time r are much smaller than this, then we'll also get an upper bound on the size of the largest component. Okay, so if this size over n theta lambda converges in probability to 0, then it follows that so C max is equal to R minus L with high probability. And so C max over n theta lambda will converge in probability to 1. Okay, is that clear? So we just want to show that that the component alive at you know, this finishes the proof that the component alive at time g, the component explored between times L and R, really is the largest component. And then we can just invoke our law of large numbers for that size R minus L. Okay, so you know, now we use that, you know, R is, you know, our argument up here says that R is bigger than n minus n prime with high probability. Okay, so the remaining graph after time is n prime with high probability. Okay, and so it suffices to show that the largest component of G n prime p over n theta lambda converges to 0 in probability. Okay, and so let's prove that. I'll just use. So what do we need to do to understand the largest component here? Well, this is this graph, right, is a Erish-Renyi random graph, but now with a different size, right? So we'd like to understand whether this graph looks subcritical or supercritical. So we need to relate p to n prime rather than to n, right? And so to relate p to n prime, I'll just remark that, so we have p is lambda over n, right? Which we can write as lambda over n prime times 1 minus delta theta lambda. Okay, so that's just using that, sorry, this is I've changed from hat to prime. These are all hats. Okay, so that's just using the definition of n hat. I've factored that out. Okay, and so I can write that as lambda over so lambda times 1 minus theta lambda over n hat, and then plus I guess delta lambda delta theta lambda over n hat. Okay, and right, so this term, right, is lambda hat over n hat, where lambda hat is the dual parameter for a Poisson lambda branching process. Okay, and so lambda is here. Lambda is 1 plus epsilon, which we know is at most some absolute bound a. Okay, and this implies so that lambda hat is at most 1 minus order epsilon. I won't use theta. So it's the most 1 minus alpha epsilon for some alpha greater than 0. So uniformly in epsilon between or lambda between 1 and a. Okay, so this is just saying that when you take a supercritical Poisson process, then its dual parameter looks sort of uniformly subcritical to the same order. Okay, so that means that this. So let's bring that down. So that tells us that p is at most 1 minus alpha epsilon over n hat, and then we have a term here which so we said that theta, so lambda is at most a. We said that theta of lambda was on the order of epsilon, uniformly in the range of lambda we're considering, and we can choose delta as small as we like. Okay, so here we have, so the numerator here looks like something of order epsilon, and then we can make times a constant that we're free to choose. Okay, so plus delta times something of order epsilon over n hat. Okay, and so we can make that at most 1 minus, say, alpha over 2 epsilon over n hat, just by choosing delta sufficiently small. Okay, so that argument is to sort of just to re-express P in terms of n hat and see that P now looks like a subcritical branch, a subcritical parameter relative to the size of the remaining graph. Okay, so now we can just, with this bound, we can use the sort of naive methodology that we already developed for studying for bounding component sizes from above in the remaining graph. Okay, so if we look at the probability that the largest component size of Gn hat P is bigger than S, okay, we know that's at most n over S times the probability that a single component in that graph has size bigger than S. And we can bound this by the probability that a Poisson bien-aimé tree with parameter 1 minus alpha over 2 epsilon has size bigger than S. Okay. So that's, and now we can bound that just using Markov's inequality. So n over S squared times the expected size of such a tree. And we know the expected size of such a tree just by summing the generation levels is 1 over, so Poisson 1 minus, C, you get size 1 over C. So this is n over S squared times 1 over alpha over 2 times epsilon. Okay, and now finally, let's take S equal to G, and we get that the probability that there's a component in the remaining graph which has size bigger than G is at most, so so let's just, the alpha over 2 term is just a constant, so let's write order 1 times n over G squared times 1 over epsilon. Okay, and that's order 1 times n over, remember, so G was, here's G. Okay, so G squared is omega n squared n over epsilon. Okay, so we have omega n squared n over epsilon, okay, times epsilon. And all we're left with is order 1 over omega n squared, which tends to 0. Okay, so so there's, there's a fair number of parameters in this proof. Some of them are going to recur, particularly G. So, I hope that wasn't too confusing, but let's quickly recap the structure of the proof we just did. Okay, we said that, so effectively we just said that because G is much smaller than n theta lambda, the size of this component is a good lower bound on the size of the largest component. And also before time G, we only explore small components. And then after time D, the graph looks subcritical. And in fact, it looks subcritical enough that our naive bound from the first lectures on random graphs for the sizes of subcritical components that just uses, effectively just uses the relation between typical and extreme components and Markov's inequality, is already enough to say that everything that comes after that point is small. Okay, so that's that sort of takes care of everything about the proof of the law of large numbers, except really understanding what happens in this time interval between when we discover a large component and when we finish discovering it. Okay, so that's where we really need to show that this process S is going to reasonably closely track the function f, this gap function here. so that, you know, it doesn't make a bunch of small components. We want it to make one big component. Okay, so there's a fair comment in the chat. I'm a bit lost with just how many parameters there are and how they're all defined. Okay, so let's just remind ourselves of that. So we have the graph we're looking at is g n lambda over n. Okay, and lambda we wrote as 1 plus epsilon. Okay, and now so theta of lambda is the probability that a Poisson lambda branching process is infinite. Okay, and it's basically epsilon. Okay, so in this up to constant factors, theta of lambda is the same as epsilon for the range of epsilon that we're considering. Okay, so lambda is in 1a here. Okay, and now we also, so we needed that epsilon n to the third tends to infinity. Okay, and then we took some other function omega which tends to infinity, which I want it to tend to infinity much more slowly than this. So if you want, you could think of omega as being like epsilon n to the third to the sixth, or log, so I want it to be much smaller than this. And in particular, you could, if it helps to think about it this way, you could take omega to be log of epsilon n to the third. That would work for everything I'm going to tell you. Okay. And now, so there's this time that it took the process to get going, which we saw sort of featured quite naturally in the end in the bound. So this time G, okay, so G was omega n root n over epsilon. Okay, and what we saw from this argument is that the naive upper bound on the size of the largest component explored after time d here was precisely of order root n over epsilon. Okay, so when you just when you use the simplest upper bound on what happens after we hope to explore this big guy, then it gives you a bound of order into the epsilon, and we just take something that grows faster than that. That's why we multiply by omega to get a bound that holds with high probability. Okay, so that's what G is doing for us, and happily, so G has the property that it's little o of epsilon n, which means that we can also use it to say that what happens sort of before this time has a negligible impact on the size of the component that we explore between these two times. Okay, and I guess the last thing I defined was D, which was n theta lambda. Okay, and I use G and D for this just based on sort of the French, so gauche and droite. Okay, so they're going to be the left and right endpoints of the interval. Okay, so that's that. I think that's all the notation I've defined so far, and yeah, I know it's a lot, but there won't be very much more. I mean, there won't be very many more terms anyway. Okay, but we do need to analyze the walk S, and that will take a bit of thought. Any other questions before we? So our goal now is to show that R minus L over D or over n theta lambda converges in probability to 1. Okay, and because since L is little o of n theta lambda, this is equivalent to showing that R over n theta lambda converges in probability to 1. So L and R, if you've if you've forgotten, these are just the times at which the times at which the component alive at time G, the exploration of that component start and end. Okay. Okay. So that's where we're headed. So our approach to this is going to be to show that the walk S is almost a martingale. And then analyze the martingale. And then bound the error between the martingale and S. Okay. So let's, what's the key to finding a martingale? It's understanding how the conditional expectation of the process changes in a given step, right? So, so let's recall we'd written Ft for the sigma algebra generated by the first time t of the process. Okay, and let's look at one of the differences. So remember, so St is the sum of from 1 to t of xi. Okay, so if we want to find a martingale, it's natural to study the sort of martingale differences. So let's look at dt for the expected value of xt given ft minus 1. Okay, so working this out sort of will tell us what the martingale differences are. Okay, and we can work out quite a nice identity for d in terms of s and kappa. So this is p n minus t minus st minus kappa t plus 1 minus 1. Okay, so this looks long, but let's just parse it for a second. Okay, remember each of these corresponds to an exploration step of the process. Okay, so this expression here is really telling us about how much there is left for us to explore. That's what this is doing, and then each of the vertices that's left to explore gets discovered with probability p. Okay, and then the minus 1 was just because we always subtract 1, I mean, in the definition of x to account for the vertex that gets explored at that step. Okay, so this is, so this, what you can, if you remember what the process is doing, then you can really see this was the number of active vertices effectively. So this is almost just straight from the definition just by looking at it, but I will verify this in more detail than that. So so what do we have conditionally given ft? Okay, so what's x t plus 1? So I'll add 1 so I don't have to carry around the minus 1. So that's the size of vt, the neighborhood of vt plus 1 intersection ut. Okay, and we said that this was binomially distributed with parameters ut prime and p. Remember, the only difference between ut and ut prime was that sometimes we had to subtract off one vertex if we just finished exploring a component. Okay, so so the size of ut prime here is the size of ut unless we just finished exploring a component. So that's when the active set is empty. Okay, and we could also write that as ut minus kappa t plus 1 minus kappa t, because when we finish exploring a component, the number of components we've seen goes up. Okay, so then what's dt plus 1 then? Well, it's this expected value xt plus 1 given f of t, right? That's the expected value of this guy minus 1 given f of t. That's just size of ut prime p minus 1. And now if we plug in the expression we just derived for the size of ut prime, then that's so ut minus kappa t minus 1, kappa t plus 1 minus kappa t. P minus 1. Okay, but now the size of, remember the size of, so the unexplored set has size, so n minus t minus the active set, right? Because at any given time, our exploration process partitions the vertices into 3 groups: active, unexplored, and explored, and the explored set just had size t. Okay, but we also saw that the size of the active set was just s plus kappa. Okay, so this is s minus st minus kappa t. Okay, and so if you just plug that in to here, then you get n minus t minus st minus kappa t plus 1 p minus 1. Okay, so that's how this process. I mean, maybe this doesn't look all that friendly of a description for how the increments evolve conditionally, but it's going to let us pretty straightforwardly find a martingale. Okay, so by looking at the difference between x and its expected value now. So so here's almost a martingale, not quite. So if I write delta t for the difference between x and its conditional expected value, okay, which is again a natural thing to do if I'm looking for a martingale. Okay, then I can write st minus the curve xt that we were thinking it ought to track as the sum I at most t 1 minus p to the t minus I times delta t minus p kappa I. Okay. And so now the thing that basically is the martingale. So if I set so s tilde to be xt plus the sum of 1 minus p to t minus I, just delta I, ignoring this this term that comes from the connected components, then the difference between st and st tilde is at most pt kappa t. Okay, and so so here is effectively where a martingale is hiding. Okay, because okay, there's something to take care of in terms of these corrections. But effectively, you see something that looks like a sum of Martingale differences here, right? Because each of these is going to have conditional expected value 0 given ft minus 1. Okay, so these fi look like martingale differences, and so this s looks very close to a martingale, and then by analyzing that martingale, we can and bounding its fluctuations, we can control the fluctuations of s around x, right? In some sense, the whole goal is understanding the fluctuations of this difference here, because we're trying to show that s closely tracks x, right? Or f, but f and x are basically the same. Okay, so this difference is really very much like it's at the heart of what we're trying to prove. Okay, is any questions about the corollary statement or more generally? Okay, so let's first prove this identity and then bound this error here. Okay, so we have st plus 1 is st plus xt plus 1, which we can write as st plus delta plus d, because delta plus d is equal to x. Okay, and now we can use the identity we derived for d, right, which was just up here, to write that as, so n minus t minus st minus kappa t plus 1 times p minus 1. Okay, so let me rearrange that just a tiny bit, because I see a pst here that I'd like to combine with the st. So that gives me 1 minus p st plus delta t plus 1, and then plus pn minus t minus p kappa t plus 1 minus 1. Okay, and then if I'm interested in looking at this difference. So and I now have a recurrence for s. So let me derive a similar recurrence for x. Okay, so xt plus 1. If I subtract off 1 minus p xt, that's remember what x is, right? So xt is n minus t minus n 1 minus p to the t. Okay, so this is n minus t minus 1 minus n 1 minus p to the t plus 1 minus 1 minus p n minus t minus n 1 minus p to the t. Okay, and if I just collect terms, then I get p n minus t minus 1. Right, so there's the 1 minus p combines with this to cancel this term, and then I have n minus t minus 1 minus p n minus t with a 1 left over. Okay, and so that tells me that xt plus 1 is 1 minus p xt plus p n minus t minus 1, which looks, quite a lot like the recurrence for s, right? Okay, and so if I just subtract those two, then I get an affine recurrence for the difference. That tells me that st plus 1 minus xt plus 1 is 1 minus p, so st minus xt. And then I still have this delta t plus 1 minus p n minus t, right? There was both terms had a minus 1, so that canceled. Okay, and I forgot something. There's a kappa, p kappa t plus 1 as well that that I've, sorry, the Pn minus T cancels, but I'm left with a P kappa T plus 1. Okay. Right. So this is just an affine recurrence for this difference, right? So the difference between, so this is constant, this evaluated at T plus 1 is constant times this evaluated at T plus a linear term. Okay, so that's just a standard recurrence relation. So this recurrence gives the identity for ST. Okay, you just get the this linear term, with this sort of geometric decay. Okay, and then so that gives us this nice identity for the difference we're interested in. Okay, and the second part of the corollary is effectively saying that we can ignore the term that is random. Well, rather, we can ignore the term related to the number of connected components and get some reasonable upper bound on how much that affects the difference we're interested in studying. Okay, so that's not hard at all. So for the bound, so what's the difference between ST and ST tilde? Okay, that's the so it's the difference between these two terms. Okay, and so the part in delta cancels, and all we're left with is this part in P kappa of I. So that's the sum of 1 minus P to the T minus I P kappa I at most T. Okay, and we can bound that by, well, each term in the sum individually. These are at most 1. They're all at most 1, and kappa is increasing. So each of the kappa I is at most kappa T. Okay, so that whole thing is just at most the sum of terms that are at most kappa P kappa T. So we get PT kappa T. Okay, let's pause there for a second. I'll just have a sip of water and then try to come a bit out of the rabbit hole, because I know this is a long computation, and look at where we're going. So where are we now? We have so let me just pull this process up to one of our pictures and place it there and think about it for a sec. So, this is the process we're really interested in. We hope that it's tracking this gap, which is xt, or effectively, this is basically the same as xt. We just showed that, so the thing that we hope tracks this gap is up to some error that we can hope is small. Well, I mean, P is 1 over n, so this is looking reasonably small, hopefully, as long as kappa is not too big. Okay, so up to some error we hope is small. Instead of studying instead of studying S, we could study S tilde. Okay. And now the last sort of modification we need in order to do that is to let's try to just rearrange this a little bit. By looking at S tilde minus X, all divided by 1 minus P to the T. Okay, so that's some I at most T 1 minus P to the minus I times delta I. Okay. And this is just an affine rearrangement. I haven't really changed the function at all, but now I have something quite clean, and this is actually going to end up being a martingale. Okay, so by studying this martingale here, I can then control the behavior of S tilde and then control the behavior of S. Okay, so that's where we're headed now. Okay, and I think so. The last thing I'd like to do today probably is show you that that this thing here really is a martingale, and prove a bound on its fluctuations. Okay, and then in the next lecture we'll use that to wrap up the proof of this, which will give us our law of large numbers for this regime, and then I'll talk about what happens in the critical regime, and that will actually connect in the critical regime. That will connect back to what we saw in the first part of the course about random graphs with a fixed surplus. So graphs with a bounded number of edges more than trees. Okay, so this is the object that we're now going to be interested in, because it connects to S tilde and then to S, and that's going to prove our theorem for us. Okay. So let me give myself a new page. Right, so here's the last result of the day. So let's let M be the thing I just wrote. So S tilde minus xt divided by 1 minus P to the T, which we said was also sum I from 1 to T, of 1 minus P to the minus I delta I. And remember that delta I is xi minus the expected value of xi given fi minus 1. Okay. Then so MT is a martingale. And the maximum of mi is at most t to the half in probability, and that's true so uniformly in t from 1 to n. Okay, so that means, so this means that this maximum divided by t to the half is tight, or equivalently that, for all delta we can find a k such that for all n, if I look at the well, for all n and all t at most n, if I look at the probability that this maximum is bigger than kt to the half, then that's less than delta. Okay, so that's just a rewriting of this. You can see why I prefer this notation, I think. Okay, so let's prove that. So what's the expected? Let's just check that MT is a martingale. It's not hard. So what's the expected value of MT given FT minus 1? That's the expected value sum from 1 to t, 1 minus P to the I, delta I, given FT minus 1, right? But all of these delta I are ft minus 1 measurable except for the last one, right? So they all come out of the conditional expectation. So that's the sum I from 1 up to t minus 1, 1 minus p to the, sorry, there's a minus there, minus I delta I, plus the expected value of, let me pull out the prefactor, 1 minus p to the minus t, expected value of delta t given ft minus 1. Okay, but ft is precisely a Martingale difference, so this expected value is equal to 0. Okay, so this is 0, and what's left is just mt minus 1. Okay, so mt is indeed a Martingale. And now we just want to understand its fluctuations. So I'll do that by just a variance computation and then using Dub's maximal inequality. Okay, so that part was to say that M is a Martingale. Okay, now, you know, if I given ft minus 1, we know that, so xt was this neighborhood of vi intersect ut minus 1. It's distributed as binomial ut minus 1 prime p. We've already used that this lecture. Okay, and so that says that the variance of delta t of the Martingale of this increment given ft minus 1, that looks like the variance of a binomial with parameter ut minus 1 prime p. Right? There's a shift, right? But the shift doesn't affect the variance, right? So and also this shift, you know, shifting this by this delta is a Martingale increment, so it's shifted by its expectation, but shifting by the expectation also doesn't affect the variance. So you know, just because yeah, moving random variables around doesn't affect the variance. So this is so this looks like the variance of a binomial, which is just the size times p times 1 minus p. Okay, so that's that's the variance of. I mean, that tells me about the variance of one of the terms in this sum. Okay, but now, so now I'll just use a general fact about martingales. So for any martingale MT that starts at 0, right? If the increments, if the Martingale increments are IT, I'm using m lowercase t because I mean I'm going to do a little computation. I'm going to apply it to MT, but the computation is so that I wanted to suggest that with the notation. But this variance computation is general. It works for any Martingale, so I'm writing it that way. So if IT is MT minus 1, then the variance of MT, you know, I can write that as, so that's the expected value MT squared minus the expected value of MT squared. This is 0, but by the Martingale property, okay. So that's the expected value sum I from 1 to t of II all squared. Okay, so which is the sum for ij from 1 to t just by linearity, expected value of ij. Okay, but now I claim that I only have to keep the diagonal terms here, right? And that's because if I look at, say, I less than j, then the expected value of ij is just by the Tower law, the expected value, conditional expected value ij given fj minus 1. Okay, and that's, so ii comes out because I is less than j, so this difference is fj minus 1 measurable. And then I have the expected value of ij given fj minus 1. But this is a Martingale difference. So this conditional expected value is 0. Okay. And so this whole term is 0. Okay, so that says that the off-diagonal terms here contribute 0. And so I can just write this as the sum from 1 to t of the expected value of ii squared. Okay. And now if I'd just like to re-express that as a variance. Again, by the Tower law, I can write that as the sum from 1 to t expected value of conditional expectation of ii squared given fi minus 1. Okay. But now using the Martingale property again, the expected value of ii given fi minus 1 is 0. And so I can add it in without, or subtract it without changing anything. So this is the expected value of ii squared given fi minus 1 minus the expected value of ii given fi minus 1 squared. Okay, and that's just, so here I have so the thing inside of the expectation here is the conditional variance of ii given fi minus 1. Okay, so I just have the sum from 1 to t of the expected value of the variance of ii given fi minus 1. Okay. So this is a nice general identity for a Martingale. You can compute the variance of MT by summing the expectations of the conditional variances. Okay, so let's apply that to the specific Martingale that we're interested in, which is this 1 minus p to the minus I delta I. Okay, so now so mt minus 1, this is our increment. That's 1 minus p to the minus I delta I. Okay, then this gives us that the variance of mt is the sum from 1 to t of the expected value of the variance of 1 minus p to the minus I delta I given fi minus 1. Okay, and so we can rewrite that as, so pull out a 1 minus p to the 2i because it's a variance, second moment, and then we have, we can then use our expression for the variance of delta I, which was just ui minus 1 prime p 1 minus p. Right? Because that variance delta I given fi minus 1 we derived up here. Okay, so we have a nice clean expression for that. So let's just bound this expectation very crudely by saying that the amount of the unexplored, the number of unexplored vertices is at most n. Okay, for this whole thing is at most sum from 1 to t. Sorry, there's a minus sign missing here. 1 minus p to the minus 2i, and then np 1 minus p. Okay, so that's at most, this term is getting bigger as I gets bigger because it's the 1 minus p is on the bottom here, but we can, for an upper bound, we can again say, well, I is always at most t, which is at most n. And so this whole thing is at most like tnp over 1 minus p to the 2n. Okay, and now because p is only constant over n at most, it's at most a over n, this thing is just looking like a constant on the bottom at worst. Okay, so this whole thing, and also np is also at most a constant on the top here. So this whole thing is looking like at most ct, where c is a constant, depending, only on our bound on P, so only on A. Okay. So we now have a martingale, and we've bounded the variance. So finishing up is very easy. So so by doob, so it follows that for any t at most n and delta positive, if we take so k to be this constant c we had a second ago over delta to the half, then the probability that the maximum value of mi for I at most t is bigger than kt to the half is at most the variance of m of t divided by k squared t. And now you just plug in our upper bound on the variance ct and the definition of k together. This is at most delta. Okay, and so that's precisely the statement that we needed. The maximum I at most t mi is order root t in probability. Okay. So let's see where that leaves us and what we have left to do for tomorrow. Okay. So so this is sort of a recap. Okay. So so remember that we I'm going to actually grab it from up here because I'm worried about a -1. Right. So we're in the process of trying to show that this difference r minus L is basically n theta of lambda. That's the goal still. Okay. And because so we know that S of L will be minus Z, S of R will be minus Z minus 1. That's what the process S looks like at those times. And we're trying to show that we want that S closely tracks X. Okay. And we've now seen that so S of t minus S tilde of t is at most so our bound was pt kappa pi kappa of I on that difference. Okay. And so when we take the maximum over times, that would give us pt kappa t. Okay. And then we've also just showed that that S tilde t minus xt divided by 1 minus p to the t. Okay, that was our mt. We just saw that that was order root t in probability. Okay. But now if we rearrange that, right, that says that S tilde t minus xt is order root t in probability, because just if we multiply through here, we're getting a bound on this difference, which is smaller than this. This 1 minus p is to the t is at most 1. Okay, so if we combine this bound and this bound, right, then we see that if we look at the error between st and xt, that's at most, well, we need to use the triangle inequality to control the difference between s and s tilde, and that's like at most pt kappa t. And then the difference between s tilde and x is at most root t in probability. Okay, and so now, and that was, once we did, we had to sort of think a bit to find this martingale, but once we found the martingale, that analysis was really quite easy. So now we have some upper bound on the difference that we're interested in, which has one part which is sort of coming from the martingale, and one part which we still need to analyze to understand, which involves understanding the number of connected components at the times that we're interested in. Okay, so to finish the proof, so we need to do two things. When are we interested in applying this bound? We're interested in applying it at the process, to understand the component that's alive at time g. Okay. Well, so then that tells us something about this error term on the right. This kappa is going to be kappa of g, basically. So we'd like to understand. So to get a good bound, we need to bound kappa of g, and then finish the analysis of xt or of ft to see that our bounds really do imply that R minus L is like n theta lambda. Okay, so I write things this way just because fundamentally all that's left probabilistically is this step of bounding the number of components we've explored by time g. That will give us an error, and then all the rest is just understanding the function that S is tracking, because the bounds will be tight enough to conclude that way. Okay, so so I think that's a good spot to leave it for today. I know there's a lot of notation. I'm sorry about that. I wanted to give you this proof because this approach via tracking the exploration process really is the way to understand what happens when you actually want to understand right at criticality. Also, with the pieces that I've showed you, you can already see that, fundamentally what we've ended up doing is controlling S by finding an associated martingale. So if you want to make finer statements about the behavior of S using this approach, you just can make finer statements about the behavior of the martingale. So in particular, I proved one bound. If you wanted to show a central limit theorem for S rather than a law of large numbers, you could just try to control the error for when this component size starts and ends in a little more detail, and you would have your central limit theorem right away. Okay, so there is a certain amount of pain involved in all the definitions, but the payoff is that we have quite a robust technique for understanding a lot of fine information about the component size and even structure in the random graph. Okay, so I would suggest, since there is a lot of notation and I need to use it, that you take, all of this is written up in full detail in the notes. So, take a look at that to refresh on what we did today before tomorrow's lecture, and then we'll polish things off tomorrow. So thanks everyone for your attention.